at the same frequency. So they take a sound that's like this, and then they just make it louder. But it's still the same frequency. Just gives the sound a higher amplitude, while others, we talked about how some people, they become less sensitive to certain frequencies. So it's not that they can't pick up the volume, it's just that they can't hear certain sounds of certain frequencies. So other hearing aids will actually modulate the frequency. And they might not do anything to the actual amplitude, only the frequency. So those hearing aids, for example, might take a sound like that, and instead of making it louder, they just give it a higher frequency. So these two sound waves have the same amplitude, but this one has a much higher frequency. Whereas these two sound waves have been amplified, like this one's quiet, this one's loud, but they're at the same pitch, or the same frequency. And so hearing aids can do either of those, or a combination of it. Then cochlear implants. Talk about this, I'll show you a video. They send an electrical signal to the brain via the auditory nerve. So it's different from a hearing aid. It doesn't actually take the sound and just make it louder or change it. It takes the sound and it translates it into an electrical signal, which plugs right into your brain. And then your brain, after some time, will learn to interpret that electrical signal. I have a video of a little kid that got a cochlear implant. Pull it up here. Job. Help a lot of people. All right. Ultrasound imaging. I know we have some ultrasound techs, and I'm sure that y'all learn a lot about ultrasound, right? You have classes that are just on ultrasound?
No, not here.
Not here, but you will take them? Yeah. So it's a handheld device. It's a very high frequency sound beyond the sonic part of the spectrum. Oh, let's see, it's about 1 to 20 million hertz. So that's megahertz. 1 to 20 million. And remember, we can hear up to 20,000 hertz. So it's a good factor of 10 above what we can hear. Or, excuse me, yeah, a factor of 10 above what we can hear. No, factor of 100 or so. It emits these, and then some of them are reflected back. The device detects the reflected waves and it calculates a penetration depth. So mother's belly, baby, inside there, you have this device that you put on top of it, and it emits sound waves. Boop, boop, boop. And then based on the structures that it bounces off of, in this case, a baby, they'll come back, but they'll come back different. So you'll have a sound wave that will bounce off of the arm, and it'll just travel this distance. And then you'll have a sound wave that bounces off the torso, and it'll travel a longer distance. And the device measures those returning sound waves, measures the time that it takes for those sound waves to return. This one, coming off the arm, will take a shorter amount of time. Coming off the torso or the head might take a longer amount of time. And it uses those times to return back to the device, basically a microphone, to detect that ultrasound waves. And it shows a picture. It calculates a picture for what it is that you're trying to image. Ultrasound imagers can also measure real-time motion. including babies. You can look at blood flow in a person. They're a nice device to use because they're non-invasive and they don't really damage. The sound waves don't damage the tissue. Don't worry about this. The resolution for this is based on the frequency. The resolution is about the same as the wavelength. Remember the relationship between frequency and wavelength, that if our frequency goes up, then our wavelength goes down and vice versa. So if I have a frequency of 3 million hertz and a speed of 1,500 meters per second, this is the speed of sound, that's close to what it is in water, I think. It's about equal to what it is in water. So for example, if you're imaging something in the human body, then we could calculate that the wavelength is about 0.0005 meters, which is equivalent to 0.5 millimeters. So with 3 million hertz, a 3 megahertz ultrasound, you can get a resolution of not a half a meter, half a millimeter. And you know, a millimeter is pretty small. A centimeter is about the width of your pinky. A millimeter is 1/10 of that. So, I don't know, it's sort of like your fingernail coming off if you have shortish fingernails. That's about a millimeter. And you're getting a resolution, meaning you can see details on this, whatever it is that you're imaging, baby or something inside your body, down to a half a millimeter. That's remarkable, don't you think? That's really fine detail. You've seen ultrasound imaging, right, of babies? It's pretty cool. You can see a lot on what's going on in there, in their body. Not just for imaging, it can also be used to heat the tissue. For restorative purposes, ablation of cancerous tissue, and breaking up kidney stones. You can use it for other things too. Any of you athletes, they ever use ultrasound for, yeah? They do ultrasound? Do they do ultrasound or do they do electric, like put electrodes on you? They do both of those. Okay. I've never done that. Yeah, okay. All right, let's try some of these questions. Do the one on the left first. Remember that intensity is equal to power divided by area. So as I go out, my intensity will be affected by the area that energy is being spread over. You're 1 meter, then you move twice as far away to 2 meters. What is the new intensity? All right, let's just do a few more seconds. And we have more than 26 here. Let's stop at 55. Okay, good. D is right. I is equal to P over A. But remember that A is proportional to R squared. In fact, the area is equal to 4 pi R squared. That's the area of a sphere. And when you have sound that's going out, it propagates out into this spherical shape. And so I can write that expression as P over 4 pi R squared. So I have this inverse square law. If I double, which is what I'm going from 1 meter to 2 meters. So I write a 2 here, not because I'm going to 2 meters, but because I'm going from 1 meter to 2 meters. But I'm doubling the distance. Not because this is 2 meters, but I'm doubling the distance. It would be the same if I was going from 2 meters to what? 4 meters. If I was going from 2 to 4, then I would also write a 2 right here. So it's only 2 here because I'm doubling that number, going from 1 to 2. And then if I have a 2 in the denominator, because it's squared, I get a 1/4 over here. So my intensity is down by a factor of 1/4. Okay? Probably going to see a question, something similar to that. Different numbers, of course, but a similar idea. Y'all could do that right for me? Yeah. Yes. All right. Let's try the one on the right. Damage to the cochlea is usually a result of what? What is the answer to that question? Do y'all know the answer? Did I tell you the answer? I was in the book. I don't know what the answer is. What's the answer? Loss of hair cells? Oh, did I just say that out loud? D. Yeah, I think those other things could cause it too. All right. Let's stop at 43. Answer's D. Okay, yeah. D. D. Answer's D. Sorry, I wrote the question. It should make sense to me. Oh, come on. Y'all didn't trust me? Like somebody still thought it was B? All right. Oh, we have a couple more. Next page. An intensity is defined as which of these? Stop at 22. 22. Good. D is right. It's power divided by area. That's on your equation sheet, but you need to know what the variables mean. That P over A is power and area. And then you also need to know what is the name of a lady with one leg? What is it? You don't know, do you? No, not Peggy. Eileen. All right, which of these is the lowest intensity of a sound that a person can hear? Remember we had our threshold of hearing and threshold of pain. What is the lowest that you can hear? All right, doing really great. I'm going to stop at 28. Oh, look at y'all, 100%. Yeah, so 10 to the minus 12th, that's hearing. And remember, the threshold of pain is a full trillion times louder. So this is our threshold of pain. But you should never really get to a threshold of pain with your hearing. Really, you need to protect your ears because every little bit of damage that you have to your ear, it never comes back. So take care of your ears. Wear ear protection. If you go to a concert, take earplugs. Even if your friends call you a dork, like still just say, I don't care. I want to hear when I'm 80 years old. Huh? What? Right. You would lose your hearing.
You would, then I'd have losing your whole ear.
That would be terrible. What did the janitor say when he jumped out of the closet? Surprise! 50 decibels is how many times as intense as 30 decibels? All right, let's stop at 28. Okay, good. C is right. So the way we do this is that first I would say 50 minus 30, and the difference in that is 20 dB. And then I really just divide by 10 and take the exponent. So it's like I say 10 to the 20, but really I don't put this 0 on, so I just say 10 to the 2. Then I just take this number and I raise it by that exponent. I raise 10 by that exponent, okay? So C is the right answer, 100. If it was 50 and 20, what would be the answer? Be 1,000. Yeah, if it was 50 and 10, it'd be 10,000. See, easy. Decibels easy. I just really want you to understand that decibels, that we use them because they cover a large range of sounds. So here, even though I'm separated only by 20 dB, only by 20 decibels, but these sounds are really 100 times more intense. Then the 50 decibel is 100 times more intense than the 30 decibel. And because the human ear has such a huge range of hearing, 1 trillion times the intensity that we can hear from the lowest to the loudest, that we express decibels on a logarithmic scale, where it doesn't go linearly, that it goes logarithmically by factors of 10. Let's try this last one. One of you, I think, has a roommate, right? With Claire, was that you have a roommate? No.
Oh, me?
Yeah, Maya? They let you use them, your roommate?
Every day.
Are you serious?
Yeah, like every day.
Good friend, huh? I need some too.
I need some clients for that.
I need. All right. Now we'll stop at 32.
Really smart.
Okay, D. Selecting out. Okay, so no, it's not selecting out particular frequencies. What the noise-canceling headphones do is they operate by this interference of waves. Interference of waves says that when I have 2 waves that are set up like this and I add them up, that they give me nothing, that it all goes away. And that's just the opposite, remember, of what the whales did. What the whales did is that they made multiple waves, and when they added them up, they got a bigger wave. Interference can go both ways. I can have, this is called constructive interference, where they constructively add up. And then this is called destructive interference. You don't need to know those words, but you do need to know interference. So these noise-canceling headphones, they take one waveform, which is your noise, whatever, the dog barking, whatever that is not your music or whatever you're listening to, and then it creates another sound that's exactly the opposite of that sound. And so it's not actually taking sound away, it's giving you another sound. And it's putting it in your ear, and inside your auditory canal, that sound is mixing up with the sound of the dog barking, and it makes it go completely away. It's kind of cool. All right, I think that's the end of that chapter, right? Yeah. Lots of stuff in that chapter, so make sure that you're reviewing it over the next week, along with the work and energy chapter. These chapters, you're right, they have a lot of content. I would read through the books, the chapters in the book, and review the notes, and look at the old tests. And I will check to make sure that I have all the exams. It's not found. All right. I sent myself a message, so I'll remember to take a look at it. It might take me a day or so to get to it. I'm sorry. I apologize. I know y'all use those, right? Y'all use those old quizzes? Remember, your tests are different, okay? Like you've had, the last test was different from previous tests, but they're very, very similar. So it's still useful for you to review those old testing quizzes, right? Y'all find that they're similar? They are similar. They cover the same material, and so the questions, you can only ask a question so many ways.
Yeah.
All right, let's look at charges. So we'll get into this chapter on variety of uses of electricity for human performance, for understanding the body, for treating the body, and then we'll also look at the nervous system and how the body uses electricity to convey information, things about your senses, things going on in your brain, lots of electrical things going on in your body, lots of charges in your body, and so we'll talk about those. They get fairly complex, and I'm sure you cover them in more detail in anatomy. You cover the nervous system in anatomy? All right, but we'll do it on a surface level. Charge is a fundamental property of matter. We really only have two fundamental properties. That's charge and then also mass. So as far as matter is concerned, we describe its charge and we describe its mass. The fundamental unit of charge we call E. So the fundamental unit of charge is E, 1E. The unit for that fundamental unit, so this isn't, I don't mean like this is the unit for the quantity, like we've used kilograms and seconds. It's not that kind of unit. It means like the fundamental division of charge, or the fundamental quantity of charge, is 1E. And the unit for that, like the dimension, is in coulombs. Now 1E has a value. The value for 1E is 1.6 times 10 to the minus 19 coulombs. This is abbreviated capital C. So the fundamental unit of charge, again, not a dimension, but it's more like a division of charge or a quantity of charge. That fundamental unit of charge is this value, and that value is the charge on an electron or a proton. So this 1E is the charge on an electron or proton. With one difference. An electron has a negative charge and a proton has a positive charge. We can talk about the charge of a proton or an electron or a neutron in terms of this. So the charge of one electron is negative 1E, which is equivalent to negative 1.6 times 10 to the minus 19. The charge of one proton is positive 1E, which is positive 1.6 times 10 to the minus 19. And then the charge of one neutron, neutrons will come back in the nuclear chapter. They'll become fairly important, but they're not that important here. The reason they're not important is because they don't have any charge. Okay, so there's 0E, which is equal, of course, to 0 coulombs. One of the properties of charge is that it's quantized. If this is the fundamental division of charge, charge can only come in these quantities. So you can't have a particle with just half E charge. So I can't have a particle with 0.8 times 10 to the minus 16, 10 to the minus 19 coulombs. So for example, if I have two protons, that would have a charge of 3.2, that's 1.6 times 2, times 10 to the minus 19 coulombs. If I have 3 electrons, that would be equal to negative 4.8 times 10 to the minus 19. But for example, if I had, I don't know, 4.0 times 10 to the minus 19 coulombs for a charge, then I would say that that is not possible. If you told me that you had a charge with that value of 4.0 times 10 to the minus 19, I would say that you were joking around with me, that that's just not possible. Because what that means is that I have somewhere between 2 protons or 3 protons, right? Because 2 protons is 3.2. 3 protons would be positive 4.8. And so I can't have a charge that's 4.0 times 10 to the minus 19. Yeah.
I understand this part. The red.
Yeah.
Let's go back to the blue part and explain it like we're in kindergarten. That sounds like a really good idea.
About the division of
Yeah,
charge?
you also can. What do you mean?
Can you, what do you mean, what I
What
mean?
do you mean?
Like, what does a division mean?
Like, yeah, I don't know.
Charge comes in discrete quantities, right? Because our charges are made up of electrons and protons. That I can have 1 electron, I can have 2 electrons, I can have 3 electrons, but I can't have 1.5 electrons. And that quantity is this fundamental division or unit of charge.
Okay.
Division, like the quantities are divided up into a particular
That means that
set.
they only come in whole.
They only come in wholes, right? But they're not integers, right? They're decimal numbers, but they only come as an integer number of these quantities. So I can have 1.6, I can have 3.2, I can have 4.8, I can have, what's after that, 5.4. I can have those set values of charge, but I can't have anything in between. Is that better? That's not the kindergarten explanation, but I think it's true nonetheless. First grade. Okay? You're welcome. It's my job. All atoms have charges. Right? They exist of protons down in the middle, and then you have these electrons that are zooming around. You also have some neutrons that make up the particle, but just right now we're worried about the electrons and protons. But most are typically neutral. And what that means when they're neutral is that they have equal numbers of electrons and protons. So if you think about your periodic table, you know, hydrogen has 1 proton, so it'll have 1 electron that's neutral. Helium, 2 protons, 2 electrons, and on and on. Lithium, 3 protons, sodium, 11 protons, and 11 electrons. But sometimes we get atoms that are not neutral, and those are called ions. We break them into cations and negative ions. You'll have a great game. You'll win. Win. Okay? They're going to win. Because they're awesome, right? Should we do a wave, a hug wave, longitudinal wave? Bye, ladies. All right, so our cations are positive. That means if you have positive, it doesn't mean that you have extra protons. It means that you have too few electrons. By the way, the abbreviation that we use for electrons is usually E with a little negative superscript.
You put position, does that mean positive?
Positive, yes.
Oh, okay.
You're supposed to know that.
I'm trying to know a new word.
Okay, so cations are positive, anions are negative, and that means too many electrons. So for example, if I had potassium, you know which one's potassium? Okay, very good. So if I had potassium and it had, I don't know, 17 electrons, what would that be? Would it be a cation or an anion? So potassium with, we'll do it as a clicker question. If it had 17 electrons, would it be a cation or anion of potassium? Potassium is right here. If I have a potassium atom with 17 electrons, is it a cation or anion?
No, no.
It has 17 electrons. What kind of ion is it going to be? All right, let's stop at 33, 4, 5. Yeah, it'd be a cation because it would have 17 electrons and 19 protons. That's how we write protons, with an E with a positive sign. That means it has more protons than electrons, so it has an overall positive charge. So it is a cation. Atoms become charged by the removal or addition of electrons. Not protons. It's really easy. It's relatively easy for me to grab this electron and rip it away. That's what chemists do all the time. They just take electrons off of an atom and they rip it away. But it's very difficult for me to take a proton and pull it away. It's not impossible that we can remove protons from a nucleus, but it's quite difficult. And in fact, if you move the protons, if you say take magnesium and remove a proton, it's actually going to then become sodium, right? Because if I remove a proton, it changes what the element is. But if I take magnesium and I can take away an electron, then it still is magnesium. It's just now going to be a cation of magnesium, like an ion. It'll have an overall positive charge. But when we talk about atoms, when they become charged, it's not from the removal or addition of protons, because that actually changes the substance of the atom. It's by the removal or addition of electrons. Yay? Electrons are easy to take away. Protons, not so easy. In the nuclear physics chapter, we'll talk about how to change atoms. There are a few processes that we can change atoms. Interesting. You'll be like nuclear physicists then. Some of you will probably encounter nuclear medicine in the future.
Will we have periodic tables?
Yeah, of course. We'll talk about how to use it, but you probably know how to use. Some of you know how to use the periodic table. You should have had it in high school. And plus, there's some in this room. Can y'all see that? Yeah, my vision has started to go, so that's looking a little fuzzy. I used to be able to see it. You can see the red? Oh, yeah. Yeah, I can see that. All right. Charge is quantized. I talked about this. Let me just reiterate. That means it comes in particular quantities. You can have plus or minus 1e, plus or minus 2e, plus or minus 3e, and on and on. But you can't have 1.5 electrons, or you can't have 3.5 protons. You can only have 1 proton, 2 protons, 3 protons. Those are our fundamental units of charge. They're not fundamental like units like dimensions, but our fundamental divisions of charge. Conservation of charge, this is a law that says that we do not produce or destroy charge. It's just not really possible because charge is a fundamental unit of, or a fundamental property of matter that we can't, just like we can't destroy or create matter out of nothing, similarly we can't do that with charge. But we can move them around, so we simply move charges around. And we can do that with matter too, that we can take matter and we can move it from one type of phase to another, or we can divide it up into different parts. But we can't create matter just out of nothing. All right, let's try these questions. What's a positively charged atom called? let's stop at 23. Awesome. Hey, how do astronomers organize a party? They plan it. Did you know that, Sydney? Did it just come to you? Yeah. All right, so a positively charged atom, what is it, cation? Yeah, let's try the one on the right here. Yes, you do. What are the fundamental divisions of charges? 1.6 times 10 to the minus 19.
I know that.
All right, so I can't have something that's between, say, 1.6 and 3.2, because 1.6 would be 1 proton, 3.2 would be 2 protons. I can't have something in between. So which of these numbers, or are they all okay, are integer values of the fundamental unit of charge?
I don't believe it.
You're not stupid.
No, really.
No.
I'm really good at that. But I went to go get that on the graph, and I was like, no, I really think it's so.
Don't say that. I really don't like for you to say that. It's not true at all. Seriously. I had this student come to my office a set number of years ago.
Gonna sit and talk about me.
It wasn't. It was a number of years. And this student comes to my office, and she was taking physics, like this, the physics for majors. But she comes in and she just says, I can't do physics. I'm like, really? You can't do physics? She's like, yeah, I'm terrible at it. I'm gonna do really poorly in your class. I'm like, really? I said, what's your GPA? And she just looked really embarrassed. And she said, I have a 4.0 GPA. And I'm like, and you can't do physics? Really? And you know, she was my best student that semester. That's top. She was the top student from all semesters.
It's because people who can't are hard on themselves. That's why.
Yeah.
See, I'm really hard on myself, but I'm sure it's not that one.
That's not true. All right, let's stop at 213. That's not true. Not true. Right? Not true. All right, D is right. Look, so I can have 1.6. I can have 3.2. I can have 4.8. What's 4 times 1.6? 6.4. So I can have this. This would be 1 proton. This would be 2 protons. This would be 3 protons. This would be 4 protons. But this would fall in between here. So 3.something, 3.5 protons. And so that is not a valid charge because charge is quantized.
So all you're doing here is taking, like, what are you doing?
I'm multiplying 1 times 1.6, 2 times 1.6, 3 times 1.6, and 4 times 1.6. Okay.
Negative 3.2, would that be a proton or electron?
Okay, so negative 3.2 is going to be 2 electrons because it has a negative in front of it. Right, but this is for 2 protons.
Okay.
This is for 2 electrons, 2 protons. See,
Gotcha.
that's what the E plus is.
Okay. That's what you were confused.
Mhm.
I'm good now.
All right? Charge is quantized. Charge comes in discrete quantities. All right, let's look at some basic properties of how charges interact regarding the electric force. And this will be important. We'll look at cells and how cells move charges around between the cell membrane and then those processes. And a big part of that is how the forces between charges interact. So we observe electric forces between 2 or more charges. Forces, as you know, always require at least 2 bodies. That you can't have a force just with 1 body. And that's a result of Newton's third law, right? Newton's third law says that for every force, we have an equal and opposite force. So whenever I have two or more charges, I'll experience these electric forces. Not if I just have one charge. If I have one charge, it will not experience an electric force. I have to have two or more. And we have a law that describes this. This is on your equation sheet, and I won't ask you to calculate anything with it, but as we've done before, you will need to know how they're related. The variables are related. So Coulomb's law describes this force. It's KQQ over d squared. This is going to be Q1 and Q2. D is just the distance between the charges. And I have some, Q is the value of the charge. This is the charge. Remember, it's measured in coulombs. D is the distance. It's measured in meters. Notice here that F is proportional to 1 over d squared. So I have that inverse square law. Remember, the inverse square law comes up a lot in nature. It's because of the spherical symmetry. And as I go out, the area increases as 1 over d squared. K is a constant. It's Coulomb's constant. You don't even really need to know the number. I won't even write it down. It's a big number. Like charges are going to repel, and opposite charges will attract. So if I have two positive charges, these two charges are going to feel forces that are in the opposite direction. But if I have a positive and a negative charge, these two charges will feel forces that are in opposite direction, or that are attractive. These are repulsive forces, these are attractive forces. And notice too that because of Newton's third law, or Newton's third law describes this, that the magnitude of these forces are the same. Remember Newton's third law? For every force is an equal and opposite reaction force. And so anytime I have a force, like here, I'm going to have an equal and opposite reaction force here. They're always the same, even if one charge is bigger than the other. Just like with the Earth and the Moon, the Earth pulls on the Moon with a certain force, and the Moon pulls on the Earth with that same force. You see Supermoon last night? It's kind of cool. Yeah, it's just close, so it looked really big. All right. If I have multiple charges, there'll be multiple forces. So you're going to see a little bit of vectors probably on the next test. Let's imagine I have this Q4. I want to know what is the net force on Q4. Is it going to be attracted or repelled by Q1?
Repelled.
Repelled, because it's the same charge, same sign of charge. So I'll call that F1. What about Q2 and Q4? Attracted or repelled? They're attracted. So I'm going to call that F2. And then Q3 will be attracted. So that'll be F3. I wouldn't give you one like this where I'd have three vectors like this. But for example, if I just gave you Q2 and Q3, so say for example I left off Q1, which would get rid of F1, the net force, or the resultant force, for F2 and F3 together would be a force that looks like this. So that is my net force, the sum of those vectors. We talked about that a number of chapters ago. Remember, we talked about how I can move with a vector direction in this, and then also like this, but that's the same as going from here over to here, that I can add up those two vectors. And that's what I've done here. I have a vector here, F2, a vector here, F3, and the sum of those is going to be this net force vector.
So the reason that we have like F1 is because of that diagonal.
Yeah. But I just removed it because I wouldn't give you a question with 3 vectors like that. That would be more than I want to test you on.
So what would be the question right here?
It would be, what is, well, let me just make up a question for you right now. Let's see, I'd give you 3 charges, plus, minus, plus. Let's call this charge over here Q1. Let me think what the answer is. And I would ask you, what is the net force on this charge? Yeah, what is the net force on that charge? A, B, C, or D? What you want to do is you draw the vectors for each individual charge. So I know these 2 charges repel and these 2 charges attract. And then you'll pick which of those vectors represents, or more closely represents, the net force vector.
In between.
Which vector falls in between those 2 vectors? We had a similar problem with this on a previous exam, but it comes up again here. Y'all try it. Right, what's the net force? You aren't getting it. Let me show you.
Oh, wait,
Yeah. So, I'm going to draw the component vectors. So, the force between these 2 is going to look like that. And the force between these 2 will look like that. So what would be the answer? Alright, good. You're moving in the right direction, but still a number of you, about half of you.
I drew it down, but I drew it down from right here. No, it's down from right here. Yeah, I drew it wrong.
Alright. So the red lines here represent the force due to the individual pairs of charges. These 2 positive charges repel, so this one feels a force in this direction. These 2 charges attract, so it feels a force in that direction. And then I have these 2 force vectors, and I want to know which of these forces, A, B, C, or D, represents the sum of those 2 force vectors. And you can think about it. If you have, guys pulling on a box with 2 ropes, they're both pulling with forces in those directions. The net force is going to be somewhere in between. So you would pick the force that's in between those 2 component vectors. All right, looks like most of you have it. I'm going to stop here at 2:30. All right, D is right. So D is the net force vector. Might see a little bit of vectors on the next test, or not the next one, but the 3rd test. So. Okay. I want to go ahead and show you this. It's kind of cool. In fact, I'm going to go ahead and stop the recording, and we'll just, when I'm done with this, we'll call it a day. Summertime.